Hello and good morning, everyone from Canada. Thank you very much for being here with us today. So the first thing I'd love to say today is Happy New Year, and we wish you all the best to you and to yours for this upcoming 2019. And it's as well the chance for us to say thank you for your interest in the events of the IIES. And we wish to have more of your interest and be able to create more collaborations in the upcoming 2019. So today we are here in the risk assessment e-lecture series, and we are at the 10th lectures on the very interesting topics on permafrost engineering and periglacial risk. I believe that is going to be the challenge for human beings for these decades and the upcoming ones. And we are fortunate to have the interventions and participations of Dr. Lukas Arenson from BGC Engineering and University of Manitoba. So thank you very much, Dr. Arenson, for your kind acceptance. And he's in Vancouver and it's 5 a.m. in Vancouver. And thank you very much for waking up so early for us. So please give me a few more minutes so I can just talk about the background of Dr. Arenson. So he's the principal geotechnical engineer in BGC Engineering in Vancouver. So he got internationally recognized expertise in frozen soils mechanics, periglacial risk assessments, and geothermal modeling. He's as well an adjunct professor at the Civil Engineering Department at the University of Manitoba in Canada. And he received on his educations and background from the prestigious ETH in Zurich. So he received a Bachelor in Science, a Master in Engineering, and a PhD in Civil Engineering. So, and for his contributions to the permafrost engineering research and the co-region engineering, he was awarded the two prestigious awards, the Troy Peway in 2003, and the Roger Brown Memorial in 2010 for his contributions. So I'm not going to hold any time longer. I really look forward for the lectures given by Professor Arenson. So thank you very much for your kind acceptance, and I just turn back the stage to you.
Thank you very much. Let's see if I can figure this all out. My screen. So I hope you see my screen.
Yeah, perfect. Thank you.
Okay, perfect. Okay, so yeah, good morning, everyone from Vancouver or wherever you are. Good evening and good afternoon. So it's my pleasure, and I apologize if I look to my right because I'm looking over to another screen here. So I hope you don't see too much of my side here. Today I'm going to talk a little bit about permafrost engineering, periglacial risk assessments. And I won't dive too much into all the technical details, but I'd like to give you a brief overview of some of the challenges that we're going to see, because I understand we have all different backgrounds here in this lecture and where everybody's coming from, so I won't dive too much into any detail. Let's see if I can move that. Oh, no, that was not good. Sorry. Oh, sorry. Here we go. Here we go. Okay. So I apologize for that. So why are we so interested in what are the challenges laying ahead of us? It's mostly because of climate change. We're seeing that the periglacial environment, and I'll give this definitions very shortly, is changing in a way that history is no longer representative for future behavior. And if it comes to design and understanding what's going to change in the future, typically we were relying on the past or looking at historical events and try to extrapolate it to future behavior. However, this is no longer possible, so we need to find new ways on how to address what's coming in the future. In addition, from an engineering perspective, we're moving more to a risk-based design. So decisions are made based on risk, and for that we need to understand what are the hazards and what are the consequences in terms of probabilities. Climate change, in particular in these environments, is causing unprecedented rapid changes. You may have heard of all the glacier receding, and they're receding at rates that have not been occurred in the past history of the Earth. So we do not really have any precedents for what's changing. And we're also moving into more extreme locations. My project as a practitioner engineer is very much related to a lot of mining environment. And if we want to move, for example, to a greener environment, there's a lot of mining required in terms of copper, rare earth, lithium, and all that. And those resources are typically not in areas that are easy accessible. So we're going to higher elevations, we're going to the north, we're going to regions that are quite extreme in terms of their environmental conditions, very cold environment, high environments that we have not yet understood from the past. So what do I want to talk about in the next 45, 50 minutes? I want to give a brief introduction to the glacial and the periglacial environment, show its dynamics, talk some of the hazards and risks related to that with an engineering eye, and most importantly, talk about the impact of climate change that we already see and may experience in the future. Now, I'm sure most of you are aware of the glacial environment. The glacial environment, surface ice, we see here two examples of large valley glaciers, and the surface environment and these glaciers, surface ice is usually controlled by changes in air temperature and precipitation. Now, when we move to the periglacial environment, it's a little bit different. The periglacial environment, even though the term peri would imply that it is around the glacial environment, is not really the environment around the glacial environment. It is actually defined as the environment where you have freeze-thaw action. So the environment and the landscape is dominated by processes related to freezing and thawing. So here is a typical example that's from the Argentine Andes. And we see here, I hope you can see my mouse. We see a rock glacier, for example, not a glacier, and I'll get to that in a second. We have solid or jellyfluxion lobes, the indicative for ground ice. We have a little Crotalus rumpert. We have talus cones. And there's probably a lot of ground ice in these slopes here too. Sure, in this particular image, we do have a glacier up there. We have some snow patches. There can be glaciers around there, but it's not required. And what's unique about the periglacial environment, it's long-term controlled. So the temperatures in the ground and the ground ice does not react immediately to changes in the atmosphere, but over changes of decades and maybe even centuries. What does that mean is when you look at the changes in the environment that we see right now are related to changes in the atmosphere that happened a couple of decades ago. In other words, if we're looking now at climate change projections, even if we were to, let's say, stop any pollution, if even temperatures, air temperatures were no longer to rise, what we're seeing in the periglacial environment is still ongoing warming. We're going to see impact from historic warming. And it's probably only at this rate that we're seeing global climate change, the changes in the periglacial environment are only going to be even more in the future than what we've seen in the past. So we cannot look at the changes in the glacial environment and translate those to changes in the periglacial environment, because the massive changes are only here to come in the future. So it's a long-term response to atmospheric changes that we have to consider. Now, here just a very brief example of what is a rock glacier. I got this from Thomas Buche. It's a short animation, and here, I hope you can see the animation. You see, it's more like a landslide. It's a slow-moving landslide. This was 4 years of deformation, and this particular rock glacier is actually a very rapid rock glacier. We can also see that the changes are very slow here in these two satellite images. I do apologize for the resolution, but that was in 2000. And now if we're looking here, if you have a trained eye, you would see here's a little rock glacier, here's a little rock glacier. And if we're moving those forwards and backwards, these are 6 years, and you keep an eye on these two little rock glaciers, you know they haven't really changed. The only change is related to the source of the images or the geoprocessing, but georeferencing, I'm sorry. But you'll see significant changes in the glacial environment. You see how those shrunk within those 6 years. You see massive change from here. There's lots of these ice patches that disappeared over those 6 years, whereas these features have hardly changed. And that's exactly what we're expecting. So it's a very slow changing environment, but the changes are going to be here, and they kind of already locked into system for the years to come. Here's a representation of how that may look in the future from Wilfried Haberle, who published this. It's very systematic, and this is more for the Alps. But what you can see is we'll see this change in surface ice. So that's the glacial environment. That's whether it's linear or not, it's to be discussed, but that's not the point here. But we see a rapid decrease in the surface ice volume. Whereas what you call the periglacial dynamics or the subsurface, so here, this part is therefore dominated by the glacial dynamics. Now, if we look at the green line, this is the change in the subsurface ice, the ground ice of the periglacial environment. And you see it's changing at a much slower rate. And what he expects, for example, for the Alps is that about halfway into the century, we're going to have the point where we have less surface ice, but more ground ice. And if you look at this globally, this changes depending on the region. So we have regions where we already are in this periglacial dominated landscape, and we have other regions where we're probably going to be longer in this glacial dominated environment. But it's a tipping point here that we start to see this. And when we look at the hazards coming from these environments in these mountainous regions, it's an important point. We need to understand how those two environments change in the future. Now, I do apologize. I think it's the screen resolution, so it's a little bit flickering here, what you see. But what I wanted to show is that within 1 year, you can see how dramatic some of those environments change. So you can have a little glacier that there used to be a glacier, and then within 2 or 3 years, it's gone. And then the environment was periglacial environment dominated, so there was no glacier ice anymore, but it was just dry. And depending on the snow, actually some of the glacial environment can come back. So in other words, it's an extremely dynamic environment, naturally, but also engineered. So when you look at some of the construction that's going on, for example, then we see in this case where a road was built, and during the construction of this road, snow was dumped to the side, and then it was actually covered by debris. It now causes ground ice to form. Here in this case, the ground ice formed naturally due to the wind drift and the transport of dust onto glacier, onto snow first, that then morphs into ground ice, firm ground ice, and so on. So it's a very dynamic environment. Just another example where you can see ground ice, in this case Aufeis, within what you think is a dry environment, but it's actually not. There's a lot of ground ice in this particular environment. Now, I said I wouldn't go too much into technical details, but I think when we talk about permafrost and periglacial environment, I just briefly want to bring up the discussion about what is actually permafrost, and that permafrost is not the same as ground ice. But when you go back to the original definition, then permafrost as such is soil or rock with or without included water that has remained at or below 0 degrees for 2 or more years. So in other words, it's a purely time and temperature dependent definition, and it does not include whether there's ground ice in it or not. However, when we look at the hazards and then in consequences and then the risks, then typically the ground ice is of importance. But when we're looking at, for example, here, like the global permafrost map that shows where permafrost exists, obviously mostly in the northern hemisphere. We have some mountain regions as well, but the permafrost itself does not tell us anything about the hazard that comes from this environment. It's the ground ice and the thawing of the ground ice that causes mostly the hazards we have to be aware of. So as I was saying, North America, here Canada, where I am at home, over here Alaska, and then Russia, Siberia, these are the major elements where we have permafrost. And then when we go to high elevation, so we have the Tibetan Plateau here in China, where we have massive areas that are covered with permafrost. And then we got into the coastal mountains, the Rocky Mountains in North America. We do have the Andes in South America. In Europe, we have the Alps, again, mountain permafrost, and then a little bit of Scandinavia, where we have a mix between polar and mountain permafrost, or here, Svalbard. Now, typically, when you look in just a little bit of focus here in North America, we talk about continuous permafrost, where we see it everywhere, discontinuous, sporadic discontinuous, and isolated. That only means that the further north you go, the colder it is, there you find permafrost everywhere. And as you go south, or if you talk elevations, if you go to lower elevations, permafrost only exists in very localized conditions. And what we do see with climate change is that these boundaries here, they're going to move north in the northern hemisphere, south, and for example, in Antarctica in the southern hemisphere, but also to higher elevations within mountainous environments. So we'll see changes in where we can find permafrost in the future. But those changes are slow and still going to happen in the future. Now, what are the challenges? We see failing infrastructure. So, for example, we see roads that are falling apart due to challenges related to permafrost degradation. We see the environment changing, being it when you have differences in permafrost and ground ice, we see new vegetation growing, and that then attracts different animals. So the biosphere is also changing. For me as an engineer, there are uncertainties in design parameters. If I have to design something for 100 years, what does that actually mean? And then we have science, politics, agencies, and the public that are interested in what's happening within the permafrost environment. I'm just thinking of the greenhouse gas feedback. You may have heard that greenhouse gases are released, so CO2 as well as methane, from degrading permafrost. So what does that actually mean in the future? Just a couple of engineering challenges that you can see within a permafrost environment. Sinkholes, if you have that in a road, obviously a major problem. If you have this, like here in Inuvik on a runway, major problem. These roads, yes, it's not a fun ride, but that's probably less of a consequence. So when you look at a runway versus a road, consequences are different, even though the hazards may be the same. Or an abandoned railway that is obviously no longer possible to be used because of permafrost degradation. We've also seen major flooding. So this is in Russia, these two images. We have here a couple of examples. The railway to Churchill that caused massive challenges to a community in Churchill in Canada that was relying on access through railway, and it was flooded due to the changes that we see in the environment, more rain in the permafrost environment, together with the limited drainage of permafrost, we see new hazards actually coming, obviously causing major risks if a community is cut off, in this case for more than a year, to have access through rail. So everything had to be brought in by air, major impacts on costs for this community. Another example here is what in Alaska is called the frozen debris lobe. You see this feature here that is slowly creeping down to the Dalton Highway and also the TAPS, which is the Alaskan pipeline, an oil pipeline bringing oil from the oil fields on the North Slope down to the market. So if this road and the pipeline were to fail because this frozen debris lobe is causing a debris flow or a major earth flow, then that has significant consequences. So we need to understand what's happening. You see here another one with these features that originate within the periglacial environment. In Russia, as well as in the Canadian Arctic, we see a lot of new lake outburst floods, and these coming from the periglacial environment. You can see here these lakes, and there's massive ground ice underneath, and we'll see these lakes draining in, you may call it a catastrophic way, but it's actually very slow. At the same time, as you can see down here with all this earth, it transports a lot of sediments down to the downstream and puts them into the water cycle, and it can affect aquatic lives downstream of such lakes. So here's a little time-lapse video that I've received from Steve Cookell, and you're going to have here a look, and you see now this lake was emptied, and I do apologize for the flickering, but what's more important is now you see this mass of earth slowly moving. So it's because of the time lapse, it shows quite rapidly, but it's an ongoing deformation of sediments. So this just moves a couple of centimeters, maybe meters a day. So it's not a rapid moving phenomenon, but you can see here the drained lake, but it allows for massive movements of sediments that didn't happen in the past. So these are new phenomena that we've seen. Here's a close-up. Luckily, this works a little bit better. And you see, it's not a catastrophic failure, but at the same time, once it's initiated, it's pretty much impossible to stop all this transport of sediment, which can lead up in the downstream aquatic life and hydro cycles. We've also seen here, this is more in a catastrophic way, these in northeast Siberia, there's some massive mega slumps that occurred, and here we're talking about kilometers in terms of width. You can imagine if a pipeline or a road would have crossed this massive failure, then that would have had severe consequences. And Julie Morton from the UK, they've been observing more and more of these features happening, again, due to permafrost degradation and just unprecedented changes within the periglacial environment, causing major risks. Another challenge that we've seen more often is what we call Aufeis and Icing. So these are ice, and some people call it glaciation, forming in a permafrost environment where water that can now run even in the ground, because the ground is getting warmer all year round. If it surfaces in the middle of the winter, where the atmosphere is still cold, then it starts to form ice. And we've seen these icings forming near roads, near pipelines, affecting engineered structures, affecting transportation infrastructure. And again, it's because the environment is changing. We're seeing warmer permafrost conditions where suddenly water can flow in what we call talus. So we're building unfrozen channels within the periglacial environment. And once this water surfaces in the middle of the winter, it then obviously freezes. But we also see new challenges within the mountain environment. Just to bring it up, to repeat it again. So what are the challenges is really the rapidly changing environment, of which I've shown you several examples, and the lack of understanding the processes. So the next video shows a rock fall that happened within the periglacial environment in Switzerland in 2017, so 1.5 years ago. It's about 4 million cubic meter of rock that fell. And what's now interesting, I'll stop the video here. Oh, sorry. I wasn't able to stop it, yes. So you see, this was within the periglacial environment. Permafrost degradation may or may not have triggered the event, so that's not clear yet. But what I want to show is this consequence. So you see here the rock falling down, and now you see a white cloud coming in the middle of the screen. What's happening here is that this rock fell on top of a glacier, pulverized the glacier. And now when we look at the consequences, what happened, and we're soon going to see footage from a village a couple of kilometers further downstream, because that was now the consequences was a debris flow, as you can see here now. So the rockfall itself would not have triggered the debris flow, but because the rock fell on top of the glacier, where now the water was available initially in a frozen state, but because of all the energy, it then transformed it into water. Now the water was available to generate a big debris flow, mud flow, that affected severely this village. So it's all this process chains that now have to be considered when we look into the environment and how this is changing. I'm only using this graph here to quickly show how things are changing. So typically we're looking at different energy level. That's from Slaymaker 2011. He showed that if we go from a glacial landscape into a periglacial landscape, we're going through this paraglacial landscape. So that's where all the changes are going to happen. And this is really environment that we're in right now. So we're seeing these changes, but the problem is we don't really know where exactly we are and how rapid these changes are. So this is the big challenge, that the environment and the changes in energy that these landscapes are producing or working within are changing unprecedented. And that's really mainly because of climate change. And when we look at all the news related to the changes in the periglacial environment as a function of climate change, we see them everywhere and everything is related to climate change. But we've got to be careful in terms of how we address those, and is it really a climate change related problem, or is it just a problem related to the already dynamic environment? But still, when we talk about climate change within the periglacial environment, the major problems is not the change in air temperature. Unfortunately, this is the change we understand the most. But what we see is active layers changing. Permafrost is degrading, not in a uniform way. So we see sinkholes. We got coastal erosion, flooding, Aufeis, mass movements that we haven't seen before, slope instability, changes in the hydrology, changes in sediment load. So all these result in new hazard and in consequences, new risks that need to be addressed somehow. Because when we look at how the permafrost environment is built, so it's not just a single element, it's a combination of all these elements. And if you turn one, then all the other ones are affected. So that's what makes it so challenging in terms of how we address it. I'm not going to read through all these, but when you talk to northern communities in terms of what are the consequences in terms of climate change, what do they see, is the air temperature is hardly showing up. It's really, they see changes in the ice conditions. They see changes in the snow. They see changes in the rain. They see changes in the season. And all these changes must be addressed when we look at climate change and how it impacts the risks and the hazard within the periglacial environment. When you look at just from an air temperature trend, then the other thing that we're seeing is northern environment, so the northern hemisphere is warming at a much more rapid rate than the southern hemisphere. So you can see it here in this in the plot to the left, but also when you split it into the different zones. So this is just the northern 23 to 90 degree northern hemisphere. That is the more the central zone, and this is the southern hemisphere, 23 to 90 degrees south. Unfortunately, it doesn't show up that well here in this graph, but you can see this is 0.6 and this is 1.4 in terms of the y-axis. So we'll see that the changes in the northern hemisphere are probably twice the ones that we see in the southern hemisphere. So there's this Arctic amplification, which in consequences affects then the permafrost environment much more rapidly. Now, when we look into mountain environments, it's more difficult because mountains are more dominated by microclimatic events. So there it's even more challenging to project what's going to happen in the future. This graph just shows the decadal averages. I think nothing new for people here in the audience that we're seeing unprecedented changes in air temperature. But as I was indicating, it's not just the air temperature. We're seeing changes in the spring snow cover. So we have less snow, which affects the insulating effect of permafrost or the runoff. We see changes in the mean sea level, which affects northern coastlines. Or we see here changes in the sea ice extent, and that also affects northern coastlines, but it also affects wave action. There's all these chains of events that can change in the future, and that must be addressed when we're looking at potential impact. So when we want to design something, how do we do this in these cold regions? So first of all, we need to check what is the project timeline. So if we're looking, for example, at a 10-year project, that's different than if I look at the tailings dam, which should be designed for perpetuity. So what's going to change? So we need to understand what we know, and more importantly, what we don't know. What are the unknowns? And then what are the hazards and potential consequences? And since we can usually not design for everything, we need to be prepared for what happens if things change. So adaptive engineering. So we need to adapt and incorporate that into our permafrost design. Just a brief view on why timeline is so important. And when we look at the projections, so that's just the difference between the RCP 2.6 and 8.5, just on a global basis. When we design something, let's say for 2030, it doesn't really matter too much what projections you can use. You may even say, well, I can use historic trends and have a little bit of a projection. However, if I look at 2100 or even beyond, that's a major difference. If I go with RCP 8.5 or 2.6 now, based on current condition, I would definitely not go for 2.6. But some people argue, well, maybe we should look at 4.6, but well, 4.5. I doubt it. So I'm probably more in the 8.5, if at all, region. But still here, we have major uncertainties that we need to look at. Same with Arctic sea ice. So the projections are quite substantial differences when you go depending on the scenario. So if you design something for the near future, you can probably look at trends doesn't really matter what model you're using, or long-term, it's different. Now, in some cases, as I was saying, you need to design for perpetuity, well, which is a very long time. Sorry. So, yeah, which scenarios to take, what projection is best to look at. But that can be dealt with if you look into a risk-based approach, as you're all familiar with. So you just have to look at what is the natural variability in your system and what would be then the range of projections. And then you can make a probability and you can try to start talking about a quantitative risk. So if you look at the distribution of your model, of your climate projections, and then based on those projections, you can move forward and generate scenarios, then you can actually define your hazards in a probabilistic way, understanding then the vulnerability and the exposure. You obviously have to make some assumptions there, but that helps you then defining a risk for the future. And what are the sensitivities? So it's not just the mean temperatures, but we need to look at seasonal changes. We need to look at minimum and maximum temperatures. So we need to understand the extrema that are coming, because in an engineering design, you're not designing for average condition, but you're designing for, let's say, a 1 in 100 year, a 1 in a 25 year, depending on what you need to do. You need to look at precipitation. If you're designing a bridge or a culvert, you need to understand how much rain do you get? What is your IDF, so intensity, duration, frequency curve? So how often do you have certain precipitation events that can cause certain runoff that need to get under your bridge or through your culvert? But you also need to understand where is your ground ice? What is how does it change its temperature? What is the active layer thickness? Do I get more frost? For example, I was working on an airstrip. So the people need to understand how much more frost days do I get, because they need to sand the runway so that airplanes can land safely. So those are all parameters that you need to look at. And as I was indicating, we're not designing for average conditions. But when we look at air temperature, just an example of Yellowknife in Northwest Territories in Canada, we're not looking at average. So when you look at climate change projections, they based on mean annual air temperature or seasonal temperatures, and then you have a projection into the future. But reality is not this line. Reality is looking something like this. So you're dealing with a wide range of temperatures. So only because the average is telling you by 2050 or so you do have this particular temperature, that doesn't mean that it's always colder prior to this. On the contrary, you actually can reach this temperature way earlier, or even temperatures above what's being projected, because of the natural variability that you have. So you need to look at how these temperatures, how the variability change. And that's probably even more problematic. So in our current design, we're assuming that the variability stays the same, and then you add the variability to the projections in terms around mean seasonal temperatures. But again, that's a broad assumption. It may not be that way. So sometimes you have to consider that it may not be like this. When we look at hazards, rockfall, debris flows, very typically we use this so-called magnitude cumulative frequency curve. We look at the return period and the magnitude. So how frequent does an event occur with a certain volume? We get these curves. Now, in the future, we don't know where this is changing. So warmer conditions may result in actually more frequent or higher events, or both. At the same time, some hazard may disappear. So if you look, for example, at ice fall from a glacial environment, due to climate change, there's no going to be no ice fall anymore because the glacier is gone, so the ice has melted. So the hazard ice fall has disappeared, but because now you have bedrock exposed, the hazard risk rock fall may now occur. So there's a change in these two hazards. So new hazards may come, others disappear due to climate change. So what should or could be done? So if we have these frequency curves, frequency magnitude curves, then which are based on historic events, you got to be careful in looking at those because they may no longer be applicable. So we need to assess the changes in these frequencies. We need to see how the magnitude can change. And for that, we'll want to use scenarios that you run, for example, in numerical models. So you can use numerical models to better understand what are the changes in your systems. You can use advanced statistics like extreme value statistics to play with some of the environmental parameters and try to understand how are those changes. It's also important to understand and look at the rates. So how rapidly is something changing? Like how rapidly are air temperature changing, precipitation pattern changing in terms of how then the hazard from the periglacial environment affects infrastructure or other elements that you are interested in for your risk assessment. So what we typically do when we have these kind of challenges, so first of all, you're trying to understand your current risk. So you do your risk assessment for the current conditions. And then you're assessing how are the, or first of all, what are the key climate parameters? So are these elements driven by precipitation? Are these elements driven by air temperature, by wind? So what is the key parameter that is driving this event and this risk? And then we need to understand how sensitive it is. And when you change and tweak some of those parameters, how sensitive does your system react to this? Then you look at, is there new potential for new hazards? As I was indicating, if glaciers disappear, then new hazards may occur. And then you can start to look at the probability or the magnitude. Is even the material available? For example, debris flows. If you have debris flows every year, then you may not even have the material, so the soil available to cause large magnitude events. So in the past, the sediments may have accumulated for 20 years, so allowing for large debris flows to form. If we have higher precipitation events that would trigger debris flows more frequent, then you do not have enough weathering that would allow for the sediments to be available. So all these processes must be looked at, not just from a historic, but from a systematic approach. So for example, here I'm just going to run quickly through a change in the active layer. So for example, we have an ice court moraine dam that is holding back a glacial lake. It currently has an active layer of 3 meters and mean annual temperature of minus 5.3 degrees. Now, you can run a couple of them model and that tell you, okay, depending on the mean annual air temperature, I have a change in the active layer thickness. So as you can see, it's an increase. So in other words, the layer that thaws in the summer is going to be thicker, and therefore the freeboard decreases, and that can cause more water to come. So if we're adding 2 degrees in mean annual air temperature for this particular case, we have an active layer increase of about 0.5 meter, 70%. And then if we look at the lake, which is 10 hectares, quite a large lake, that's 50,000 cubic meters of additional water that may be available. So now we can look at the scenario. So an increase in the active layer likely increases the dam breach rate. So in other words, we have higher peak flows. And then we can evaluate the changes in consequences for this rapid release scenario. So if this moraine dam, which formed naturally, were to breach, then what are the consequences? So we're looking at this now from a probability perspective. So we're saying, okay, a summer that is 2 degrees warmer currently occurs every 20 years. Without going all to the details, but what the final idea is that you look at it from a probability perspective. So in other words, so the probability of these additional 50,000 cubic meter of water to be available as a consequence of active layer thickening, and again, lots of assumptions in there, and that could change then the breach rate of the dam and the peak discharge, increases from an annual probability of 5% to 33%. So this is now, in a quantitative way, we can say from currently this probability for this event to happen is going from 5% to 33%. But you also need to understand, are there changes in the consequences in the future, or that then results in new risks? But that's a step to trying to quantify changes in the risks in the future. I know this was very, very, very quick and just was rushing through, but just wanted to show you how this could be done. It's not the point of everybody to follow here in this particular example. So if we want to sum up what I've been talking about for the last 45 minutes is when we look at risks within the periglacial environment, we really need to switch to this quantitative risk assessment. And because we do need a better understanding of risks within the engineering practice. And this can be done, but we need to look at the hazards that are coming. So the environment is changing, as I've shown, so we need to look at scenarios because the historic events are really no longer representative for the future. So this first principle that we use in geoscience all the time, from just assuming that things are actually you can look at the past to predict the future, that's really no longer applicable. And what I'm proposing here is using this systematic approach that looks at different scenarios. And when you use these scenarios in a methodological way, then you can look at changes in your environment, and that then helps in better understanding quantitative risks and in the future. But it's important that we're understanding what are the key parameters. So what are the climate parameters that drive your Earth processes in the futures? And it's not the average condition, it's really the extrema. And within these extrema, how frequently do they change? And we should use different tools, as I was saying, sensitivity analysis, numerical modeling, to really project future changes within geohazards. And when you look at new geohazards, and then we need to evaluate additional consequences. So if you look at process chains, for example, like debris flow going into a lake, generating a tsunami, generating an outburst flood, all these chains, how are they going to change? Now, there is still a lot of research required because we're only starting to understand how these environments are changing, and still we see new processes like these massive sinkholes that we've seen in Siberia to form. We don't know where those are changing, in particular, those feedbacks and how the environment is changing in the future. But I am very convinced that we need to use these quantitative risk assessment to actually have better and make better decisions in the future for these challenging engineering projects that we're going to see raising in the future. But I'd like to finish off with a quote from Niels Bohr, and that's, prediction is very difficult, especially about the future, which is exactly what we need to do. So as such, use your tools that you have and the understanding of processes to make better informed decisions. I also found this article here that was talking about climate change could make Siberia an attractive place to live. I am not really sure about that, and I think we better understand the risks involved moving there in a warmer planet before we can draw those conclusions. Yes, and that ends my presentation. And thank you very much for your attention.
Awesome. Thank you very much, Dr. Arenson, for this very interesting talk. And we learned a lot about the risks that we have. So we just got one question from Professor Evans. He thank you for this extremely interesting talk and excellent visuals. For some of the extreme events, such as the sweet debris flow, were there advanced indicators of the events? And is there sufficient existing data to predict such events?
Very good question. In this particular case, yes. There had been some indication used before, and it was heavily monitored. And I think that was an advantage of being in Switzerland, which is a country that has the funds and also kind of densely populated, so that people understand much better some of those hazards and have time to monitor some of those hazards prior to the event. And there were warning signs. Unfortunately, 7 hikers got killed during this event. They may have ignored some of those warnings. They were hiking in that area when the event happened. Luckily, nobody within the village got affected. However, the debris flow itself was not projected to that extent. So it was a little bit of a surprise, but people were kind of ready to expect the debris flow. So the consequences to the village, houses were destroyed, but luckily no life lost within this. But it is a major challenge and I think we do see actually some events that have no previous signs, and you cannot monitor every square meters in the world. INSAR is a great technology, so we use more Earth observatory methods, but it's very hard. It's extremely hard.
Yeah, thank you very much. I got another question as well. Could you please elaborate a little bit the 2 scenarios, the RCP 2.6 and 8.2, on the way we should adapt any projects? For example, if I go for a project for 100 years of a mining companies, so which scenario would be better for some specific case?
I mean, right now, I would look at 8.6. So I wouldn't even worry. I mean, when you look at what's happening now globally in terms of climate change and how we're dealing with the reduction of fossil fuels, 2.6 is completely out of the question, and that's a big challenge for the planet. So 8.5. If we're lucky, we're following it. I mean, the trends are all on the extreme side, so I would.
So there is intermediate as well, right? There is 4.5, something like that. And from a perspective of an engineer, if you have to design a project, if we fall in the situation of 4.5 or we fall in the situation of 8.2, there is any big adaptations that you need to bring to the project if we go into one or the other?
Yes. So, I mean, what we're doing with larger projects, because you cannot design for all the events, but you need to be aware that you may have to come back and, let's say, raise a bridge or increase the culvert capacity. And so you want to be aware that your design may be adapted. There's a good example in Austria, which is it's a bit different, but a foundation of a mountain restaurant, which is on permafrost, and they knew exactly that the foundation will deform. So instead of building it on 4 corners or on a flat foundation, as you wish, they decided, well, the building is going to be a structure that is founded only on 3 points. So it's a whole structure that is independent and it's founded on 3 points, and we use jacks under these foundations. So what it's now allowing is that the building can settle anyway, and they didn't know how it's going to settle because it's not possible to project that. But if this corner dips, then they just every year they jack it up, put steel plates under the foundation, and now the building is flat again. So by adapting your design and incorporating the uncertainty, you can come up with actually good designs. So that's why I'm saying understanding the unknowns. So if you know that I don't know the settlements, I can design my foundation so that I can adjust it in the future. So I just want to quickly answer here, Doug Evans, on that.
Yep.
So I can see that you can use the principle on a limited scale around proposed mine, but and you're absolutely right. So if you look at pipelines, I mean, there, for example, what we're doing with pipelines is you use satellite-based monitoring, and there's this INSAR technology that can be used, and more frequently now with drones, you can fly independent drones and monitor the pipeline. But it's, I think something that we need to switch over is really, in engineering practice, we call it the observational approach, by using more monitoring, and there are extremely helpful technologies out there to understand how things are changing, because as you just indicated, we cannot design for all scenarios. But we need to, if we know it, and we can monitor and we can adjust as we go.
Awesome. Yeah, thank you very much, Dr. Arenson. I just wonder if there's any other question from the audience. So if you might have any question further on, just forward to me an email and might forward to Dr. Arenson. So thank you very much again, Dr. Arenson, for your presentations and for your time, for waking up again so early for us.
No worries, I have my coffee.
Thank you, and thank you very much for the audience for attending today. And so next week we're going to have the last lecture of the series. Is a lecture about the nanomaterial. Thank you very much. Have a good day.
Thank you.
Thank you. Bye-bye.
Everybody.